to capacitor conductors, okay. What I was a little more concerned about was the circuit part. I expected the circuit part for a good chunk of you circuit jocks to be like, oh, and for some yes, for some no.
Those damn resistors.
Yeah, getting the equivalent resistors backwards. There's a few things. This is one that I did want to point out. Just I'm looking at this stuff. It totally threw me off why it would cause angst. I don't care what the values are, but the first question was, what's the voltage across this resistor? Call it R3. What's it attached to? On the right. How's it attached?
Series.
Parallel.
What?
What's in?
This is not in series with that. But this and this, well, and this are all in parallel. There's no series here. This end, this whole thing is how many volts above this whole thing. I've seen that whole area filled up with calculations. I'm looking at that and I'm thinking, well, looks like 3 volts to me. I guess that should be like that. On the outside, you know what I'm saying? I mean, this is the type of thing I'm looking at and I'm thinking, okay, we got a bunch of engineers doing calculations without even bothering to look at it. Yeah, sometimes. But it was that sort of thing that I think not everybody, but 3/4 of the class missed what I thought was an obvious inspection question. So, not everybody. But what even made it more precarious for me is that people actually did figure out that there were 2 volts across this with this not calculated properly. Now I'm for the life of me thinking, what the F? I can't even say what the hell. So, you know, I'm not going on some rant here, but I mean, it was a couple of these things that were more concerning to me than some of the other stuff. Here's another one. This is just a use your head sort of idea, okay? So I got take me a long time to grade these things when I'm not done with them. And I already told you I took off the weekend, so I thought, oh, piece of cake. No. So we got something like this, right? Now, let me ask a simple conceptual question. Okay, so let's just call this, there's your resistor, right? There's your resistor with a load. My question is this. It's just a simple question, and again, this was not everybody, but for anybody that this was problematic, I was seriously disappointed. If the current across here is 0.3, you can calculate whatever this guy is, okay? Forget about subtracting out to get the rooster. I just get that far. Here's my question. If this is 0.6 instead of 0.3, what happens to this resistance? Is it larger or smaller than if it were 0.3? Oh, Jesus. Hard to religious reference.
Should be half as much.
It's going to be half as much.
Right.
Twice the current, half the resistance. Right? The resistance drops, I mean, you can push more current through for the same point, for the same power source. Again, just a couple simple things. You know, okay, you didn't remember the electric field along a cylinder. Okay, I can get why that one might be problematic. was some of the simple stuff that really threw me when I'm grading this, trying to get a sense of. If the rooster had more resistance when there's more current flowing through than when there's less current through, I don't know how that's physically possible. And to me, that's somebody just grinding through numbers and hoping for the best, and not even bothering to think about what the answer might mean. And for me, that's concerning because I spend so much time trying to get a sense of context. Really. So, you know, those were a couple of things that were just observations that I noted. And, you know, you have an exam, you get panicked, you know, there's a lot of stuff going on. Okay, but it was just a couple things like that that were perplexing to me. More than, you know, some of the other stuff, I knew it was going to be more technical. You either knew the drift velocity equation or you didn't. I mean, you know, I knew some of that stuff was going to be tenuous, hit or miss, if you will, depending on what you wrote down on the note card. But I thought that some of those ought to have been direct and straightforward. And that's a conceptual question. That was not a calculation question. So, but you could have done the calculation in spite of that. But regardless, it should never have been a calculation. So, anyway, just some observations. In spite of that, the average score was, so far, and I don't think it's going to go down much if it goes down at all. Honestly, I have no clue, but I don't think it's going to go down much. It might. It could go up. But in spite of that, it's still about 74% without a high score being an A. Uncurved. That's pretty damn good. So, right? I mean, it's not as high. I'd like an 85 and 90%, certainly. But I can't complain for the most part. But like I said, a couple of little things scare me. Right? I wouldn't want you out designing an electric circuit that had any sort of safety potential risk whatsoever without paying attention to what it is you're looking at, right? I mean, that's, in the end, that's the bigger picture. The engineer classes will give you all the Thevenin equivalent circuits and all that crap you ever need if you're doing electrical circuitry. I don't get it. It's understanding the physics and what's in front of you. So a couple little things like that. Yeah. Okay. So now we've got a few things that they become quite technical from a magnetism perspective. I'm going to try to crank it all in today because we have 1 week left, and I want to spend our time on some of the interesting aspects of electromagnetic induction processes. So we have to get through some of this stuff. Now, so let's start with where we left off, and that was, if I've got a wire near a second wire, and they each have a current flowing through them, the question was, if this wire is next to this wire, what is the effect on wire 1? Due to the presence of the current in wire 2. First thing we might say is, well, how would they interact? They have a net charge. They both have a net charge of 0. It's not an electrical interaction directly. It's going to be a magnetic interaction because of the current present. The question is, how does that dynamic play out? Well, if this is what is affecting this, and this is what we're looking at, then the question is, what magnetic field, or at least what's the direction of the magnetic field associated with this wire? Well, we crank out the right-hand rule, stick our thumb in the direction of the current up above, fingers going out of the board. So, if this wire is directly above this wire, we have a magnetic field that's going to be pointing out of the board at that point. It's going to be circular or cylindrical and go around in a, we call that V2. It's going to go around this wire like that. But you're going to have a magnetic field that's pointing this way with a flow of charge that's pointing that way. So what would be the direction of force? Finger in the direction of the current. Curl your other fingers in the direction of the field. Thumbs down. So the magnetic force exerted on the top wire ought to be down toward the second wire.
Wait, so it's coming out?
The field is coming out, yeah.
Yeah.
Would it be up?
Yeah,
Have it backwards?
that's what I thought.
That's right.
Finger,
Along the,
no, careful, careful. For force, it's finger in the direction of current. Curl your other fingers toward the direction of the field at that point, and your thumb is pointing in the direction of the force. So it should be down. Another way of looking at it, another way of just orienting the right-hand rule might be helpful. Thumb in the direction of the current, fingers in the direction of the field, palm in the direction of the force. I didn't learn it that way, so I don't teach it that way, but it's another way of looking at it. In other words, palm is in the direction it's being pushed. So, current, field, force. But again, I grew up with it this way, so. Heck, you take the exam, put an I on your middle finger, or on your index finger, put a B on your middle finger, and put an F on your thumb if you had to. Tattoo them, right? We live in the tat generation, so there's some tat going on there. Ink. So, it'll be down, should be down. And if nothing else, I might be able to say this. Whatever the magnitude of this force is, this is on one. I know I can make basically 3 statements about it by inspection, nothing else. And no, I'm not going to give an equation here, but I can make a couple basic statements. First of all, the interaction is going to be directly proportional to the amount of current in wire 1 because there's more flow of charge, therefore it's going to have a greater effect on that charge. Is that reasonable? Second, the more charge in this current, or the more current flowing through this wire, at some basic level, the greater the magnetic field that moving charge is going to produce in the first place. Is that a reasonable statement? So it's going to somehow be related to the magnitude of that wire as well. Whether it's attractive or repulsive, just by the amount of charge that's flowing between either of those wires, respectively. So there's no calculation here, I just want to think about what ought to be involved. And lastly, if there's a certain distance between these, for now I'm going to call it D. We'll deal with a letter at some point, maybe a little more useful. It's going to be inversely related in some way to the separation distance. I don't know if it's going to be a square, a cube, a log. All I know is that as the distance between them gets larger, the magnetic field is going to get smaller, the interaction is going to get weaker. Right? The further away any 2 systems get, the weaker their interaction. So this shouldn't be an equal, this should be a proportional. So at the very least, I can make this inference. If I couldn't remember anything else, I couldn't remember any other constant, I ought to at least be cognizant or aware of that. That was a horrible. Not to be confused with your temperature coefficient, which is different. So then the question is, we'll have them calculated. I would figure out what this magnetic field is. Okay, moving charges interact with magnetic fields. Well, those magnetic fields are produced by other moving charges. How do we figure out how to calculate that? This is how we do it. Got a wire, and I'm just going to call it I now, a certain amount of current. And that current is moving in a certain direction. And I want to know at some distance, say point P, And since I'm directly above this wire, I'm gonna say some distance y above that wire. I wanna know what is the magnetic field, vector, if you will, up here. Now, it's really an x, y value, so I probably should be a little bit more careful, but I wanna know, now let's call this p instead. Just at this particular point, it could be anywhere. It doesn't have to be symmetric in the middle, it's just gonna be something like that. Now, how do we figure out what the magnetic field is doing as a function of that current? Here's how we look at it. First of all, you start out by taking a little chunk of wire. That little chunk of wire, I'm going to call it ds just to be consistent with the textbook. In other words, every little region along the wire is going to have a certain amount of current, flowing, moving charge. And we can think of that as sort of a point where charge is moving. And that movement of charge at that little region is going to have an interaction up here. Kind of like a point charge. Think of this like a line of charge. Okay, well, now let's sort of clarify something else. Because the current's flowing in one direction, let's indicate that it's a vector pointing this way. Just because it will matter in terms of forward, backwards, plus or minus what this vector would be. It'd be either in or out, right? Or forward, depending on the direction of that. So that's the first thing. Next thing, how far away is this point P from that current element? Separation distance again, right? Somehow related to separation distance. So I'm going to call this vector here R. There's my separation distance from this element of moving charge and that point P. We've done this before with a line of charge in an electric field. Well, here's where it gets, call it nasty, I guess. Turns out that the magnetic field associated with this little region of charge, flow I should say, is related to some constant. This is why we use 4 pi times 10 to the negative 7 u naught constant, because it turns out in some cases that 4 pi cancels out anyway. But it's related to some constant times this current element. It's inversely related to the square of this separation distance. Not done yet. I want to think about this for a second. Does that look familiar? A constant times a point element divided by a separation distance squared. What? Rhymes with Coulomb's law? This is Coulomb's law. This expression is a Coulomb's law relationship for magnetic field when you express it this way. Now we got one big concern. It's a vector. So what's the direction of this thing? What do we know about magnetic fields and the relationship between it's going to be perpendicular to the plane of this stuff? Because it's going to be out or in the board. So there's a plane here associated with this element to this point. And the field is going to be perpendicular to that. So it turns out that the way we calculate it to get our signs right is we look at the direction of this point, of this vector, from there to there. And we multiply it as a scalar, or as a vector product, by the direction vector associated with the movement of the charge over this little charge element, or this little element. So basically, this just allows us, I'll put the r squared there, to get the orientation perpendicular. It's just a unit vector, so it has no magnitude value, it just keeps our direction straight. But ultimately, it's a Coulomb interaction. At least it's expressed that way. Physicists are not original. When in doubt, we try to make things look as similar in model to something else we've used before. Heat conduction, electrical conduction. Newton's second law, electrical forces. Gravitational fields, electrical fields, magnetic fields. So when in doubt, use stuff we've used before. Okay, now, to this end then, there's another way we can express this, kind of simplified a little bit, because we got that whole issue with our right hand, as most boys do. And we can say that this is related to this constant times ds divided by r squared times the cosine sine of the angle between r and ds. That would be how we calculate, well, in general, that's how you calculate the magnitude of a cross product. Now to get the direction, I'm just going to use an I, arbitrary direction, according to the right-hand rule. Now keep it straight. So I can do a direct calculation and just remind myself that the direction I'll just get by putting my finger in the direction of the current. In this case, my finger's now in the direction of the position vector, or the separation vector. Current. What do we got here? Current. Like that. Right? Not all the way up. It's not a 90-degree angle. Finger in the direction of the current. It's not a force, so you don't want to probably use your palm. But fingers in the direction of I. Curl your non-index finger in the direction of R, and your thumb's pointing in the direction of the field, which, by the way, is where we would expect it to be. Right? We already talked about that whole circular business. So we would expect it to be out of the board, so just use the right-hand rule to deal with that. So it basically would be index finger curling those fingers, and what do we got here? Of course, that was really stupid, wasn't it? Okay. Got to get your fingers in the right spot. There we go. So this would be the inside. Right? You got to make little divots there. And your thumb then, that's one kind of a thumb, should be pointing in the direction out of the board. I shouldn't be drawing this, I'm not sure. Now you're racing.
Yeah, don't even worry about it.
Alright, so there's ds. Curl your finger into R. You go in this direction, the field comes out.
Oh, that's good.
Yeah, not bad, I got it.
Much better.
Okay, that helped? A little bit better. So the question is just how you get your damn finger around. If you point this way, basically you can do this with your finger anyway, so you can kind of figure out the best way to throw that up there. Like I said, that's just what instructors, physics teachers live for, is seeing their students doing this on the final exam of the class, trying to get that right hand rule straight. Okay. Or just do a cross product. That's okay. You can set them up as determinants.
Cross R is B. Direction.
Cross R is B, if you will. But we just call it a position vector this way. A flow vector, if you will.
But then F is the weird one. The F sub B.
Okay, I'm not sure what you mean by F sub B. Magnetic force. Well, you do this to find B, and then you do it again to find F. So you gotta do it twice.
But you have to do L cross B is F?
Yeah. L cross B, S cross R, I cross R. So yeah, it's funky. They literally had to create a mathematic to deal with this stuff.
Yeah.
simultaneously with fluid mechanics and fluid physics. So it all happened in the 1870s, 1880s, 1890s, because there was no mathematics to account for it. So it's kind of cool how the vectors came about in the first place. So basically, this is how you do it. Now, that's this one element, but there's a lot more little chunks of this wire, and at every point in the wire, they're all affecting it the same way. So, as with most true physical problems, then the real question is not writing this down. That should be the easy part. The hard part then is figuring out a coordinate system so that we can assign proper values to evaluate this over all of these little ds elements. So if I want to know the magnetic field up there, and the nice thing is that the plane, as long as the wire is straight, whatever direction it's pointing, as long as the wire is straight, then the field will always be pointing in the same direction for every element. Now, if the wire's bent, you may be a little bit different, but when we can say this, life is good. So, if I want to calculate the total B, at point P, I need to evaluate all of these little dBs. Which means I need to evaluate all of these 4 pi over mu naughts ds times sine phase over r squared. And r is going to vary over the wire. I'm just going to write it this way for now. I got to evaluate this whole thing. So, easiest way to do it, I define my y direction. So let's go ahead and add an x this way, and we'll make z out of the board. I know some of you said last time that you like to have z pointing up. Let's just keep z out of the board. We've already established that z should be coming out of the board, so we'll. So, along this direction then, I'm going to bring out all the constants. And what have I already mucked up on this? I can tell by the units already. Magnetic force. What do we know about magnetic force? It's equal to I L
Cross B.
cross B. That's probably not the one. What about a solenoid? What's the magnetic field associated with the solenoid? See what I'm doing this for a second. Again, I want you to keep track of what's in front of you, because I got this damn thing backwards. I know it's backwards, but I want to show you why. From our last lab, B associated with the solenoid. I know you don't want to see it this way. It's related to mu naught I N over L, right? What does that tell us about mu naught? It's going to have, among other units, units of Tesla in the numerator, not in the denominator. Which means these are flipped. Thinking about this in terms of epsilon naught. So these need to be backwards. Apologize for that, but I can figure that out by inspection without having to memorize anything, because I know that it's going to be units that are numerator consistent with Tesla units, whatever else is going on.
It also looks more like Coulomb's law now.
Yeah, it looks more like
Yeah.
Either way, it's a calculation, but the mu naught is opposite the epsilon naught. Okay, so just kind of keep that in mind. Mu naught is in the numerator, epsilon naught is in the denominator, if you will.
What's mu naught?
Yes, not 4 pi over mu naught. Because mu naught has to have units of Tesla. And the other thing is I forgot to put my I in there. Why are units helpful? Because when you start talking and writing, and until this very moment, I haven't thought about this equation, so it took me a second to get everything lined up. So there's going to be an I in there. And again, if it's not proportional to I, we got other issues. Everything I've said is consistent, I just left an I out. And we need an I because mu naught is going to have units of Tesla per ampere meter. Just going back to magnetic field, if you will, for a solenoid, and we've done that already. We haven't figured out how to calculate it, but it has to be consistent with that. Shouldn't do that to you guys when we're just learning this, but I just happened to catch that. So we need to evaluate this whole thing. Now, I is not changing along the wire. So as I pull out constants, I'm going to pull the I out as well. So not only is mu naught over 4 pi, but I is also a constant along this wire. It doesn't get smaller as you're going along the wire. It's uniform along the wire. So I'm going to bring my I out for that wire. Now I'm left with, how do I figure out what ds is? Well, it's a length segment, a small length segment where that current's flowing through.
Yeah, it's just
It's dx in this case. What's the separation distance? Well, if we replace this with dx, and I'm going to call the origin of this 0 right there. So everything that's happening with my coordinate system is that doesn't have to be centered, but it's the closest distance from point P. So I'm going to put it just directly below point P. I'm going to put my origin there, because then I can say, well, this ds is positioned with x away, negative x, but it's going to have a value of whatever this x is, squared, plus this y squared. That's going to be the distance of this hypotenuse. So I'm going to note that the magnitude of r is going to go as x squared plus y squared. So r squared is going to go as x squared plus y squared. It doesn't matter if it's positive or negative, it's like squared anyway. So for the r squared, I'm going to rewrite it as x squared plus y squared. Now I got a sign to deal with. So for now I'm going to leave the sign this way, and we'll deal with how do we figure out what the sign is. If I left it this way, I'd be trying to evaluate something along x, but the angle is going to change as I go along x, so I cannot evaluate this expression until I figure out a way to have that kind of angle expressed in terms of the integrated variable, in this case x. So the sign of this,
Y over R.
is going to be the opposite over r.
y over root x squared.
So it's going to be y over the square root of x squared.